So we basically finished now this line spectra. And now we come to a completely different light source. So if we have an individual atom, it will always emit light with the same frequencies, or it will absorb if light comes along with just the right frequency or wavelengths, it will absorb this. This is this discrete lines. This comes because of this. We've seen only specific orbits according to Bohr. Quantum mechanically, these are different energy states with different energy. So as on a ladder, you can only take certain step heights. And this comes directly what is called from the boundary conditions. Every bound quantum system will develop such a shell structure. Even the atomic nucleus has a shell structure, molecules have a shell structure, even the proton, neutron, which are compound system of quarks, they have this type of excited states, which is called the hadron resonances. So very important concept, but not so much here. It's just what we observe is that the jump from one step of the ladder to the other step. The energy difference between this is emitted as light or absorbed as light. Or so excursion to quantum mechanics again, and now we basically go back to the very beginnings of quantum mechanics for the other light source, which is the theoretical or thought concept of blackbody. And we talk now about blackbody radiation. So blackbody in physics, it's nowadays, well, it's Black Lives Matters, and a lot of these names origins from the 19th century. When I had theoretical physics, this was occasionally a festival of political incorrect expressions. In quantum mechanics, if levels are found at the same energy, we call them degenerate. This is a Nazis word for modern arts, degenerated arts. And continued, but his historical grown language, and well, since it describes nature, one should not everything that has been touched and spoiled by somebody immediately dump. So maybe it can be cleaned and reused. Okay, so now we come to blackbody radiation. Let me share my screen. Screen 2. See this now? Now open there. Yeah. Hopefully it's still visible, otherwise I'm again wasted loads of time. So the definition of one of these black bodies, it's a hypothetical perfect absorber. So if light is shined on, it's completely absorbed. But in the same moment, also emitter of radiation. If it absorbs energy, well, obviously it will become hotter. If it emits, it will become a bit cooler. If this is now in equilibrium, we have one constant temperature. So an absolute perfect absorber, perfect emitter. What is not happening is that light shines on and is reflected. Oh, no mirrors. Experimentally, we basically made this by having a cube, and inside only a very small hole, not to disturb the system. Inside the walls color black. Then give it a certain temperature, then you measure in this little hole. The wavelength distribution. How many light particles or light waves with one given light wavelength, which is here at the bottom, is the wavelengths plotted and how many or how intense. Therefore, if we go back to this concept of photons, of light particles, you take the light field and chop it into its individual pieces like a chef would do with salad. And take one of these leftover salad pieces and say it's not possible to divide it anymore. We would be back to photons. So how many photons with the different wavelengths are here? Then we measure this for different temperatures of this black body. And what we get is basically shown here. So the wavelengths, well, for 3000 Kelvin, we don't see much. It's almost down with that. For 4000, we see getting up, having a maximum, and going down. 5000, again, going up, going down. And this here looks like a parabola that turns over. This is an exponential decay. Okay. And it seems to be always the same shape, just a different area underneath the curve. And the maximum is changing to lower and lower wavelengths, but means higher frequencies. And now, according to Planck, if you remember, the frequency multiplied with Planck's constant corresponds to an energy of the system. Therefore, energy, again, can be related to temperature. Then we get the direct proportionality between where is here the maximum of this curve in terms of the wavelengths, or at which wavelengths is the maximum found, inversely proportional to the temperature. The higher the temperature, the lower is the maximum of this curve found. So if we have now a body, like let's say our sun, then we can now, for the sun, measure this Planck spectrum. We should, of course, go above the atmosphere. And then if we can measure this Planck spectrum, what we will get for our sun is something that looks roughly like this 5000 Kelvin. Which color does our sun have? It's yellowish mostly. So it has a slight yellowish. Of course, we have to be careful because we measure now down here at the bottom of the atmosphere, or with an atmosphere that might have absorbed and changed. But if we go beyond the atmosphere, we still see it's yellowish. Remember, Betelgeuse is part of Orion last week. If you have checked it, you might have seen that it's slightly reddish. Slightly reddish. Ooh. This has a surface temperature of roughly 4000 Kelvin. Do you see the maximum where it's here situated roughly gives us what color we see? In fact, then if we go have some body with 6000, it will be roughly greenish bluish, or turquoise. If we have everything above, it will be very bluish to violet. Because there we have the most light particle with this color coming from. At this temperature color relation, every blacksmith knew about. Basically, you put the steel into the fire and waited until it has to, or made the fire to glow and whatever to make the fire hotter and hotter. Until the iron had or the steel had the right temperature to be worked on, which was obviously generations of experience. And then, which he has seen by the color. Then we took it out and hammered on it until it has been cooled down again and then heated up again. So years and years, generations of experience basically knew this relation, which is nowadays known as Wien's law. So if we observe the body of a star, the body, the color of a star, we get its surface temperature. By the way, that's the way how you measure very high temperature. You measure this Planck spectrum, what we call now a Planck spectrum, because it always has the same shape. Let's see where is the maximum. We get the temperature. If you have 7,000 degree hot body or gas, if you come along with a thermometer, you put the thermometer to hold it against, and what happens? The thermometer melts away. So that's the way to do it. You use the radiation. So this is one law, which people basically quickly established. Then, if we go, or if we look at the temperature, seems to be also related towards the area under the curve. So 4,000 Kelvin, the area is higher than for 3,000, for 5,000, it's higher than for 4,000, 6,000, certainly higher than everything. And you see how it's drastically increasing. So the number, the total number of photons is getting more and more. The total number of photons corresponds basically for one given wavelength here, directly go up here. And if you would now make bins, we would take the number of bins with their content, and we get the area. It's the Riemann definition of an integral. So this area, therefore the total intensity seems also to scale with the temperature. And we see it's obviously drastically increasing with temperature. We double the temperature, and this is certainly far, far higher than at 3,000 Kelvin, where we have almost, at least on this scale, coinciding with the x-axis. Okay. So what's plotted here, by the way, that's the radiancy, that's some kind of the intensity denormalized for the surface, and the picometer. So that's from the wavelengths. Okay. This Wien's law we directly had. By the way, this is then something when I finish with this here, this proportionality. So of this temperature, the area underneath is directly proportional to the force power of the temperature, as well as on the surface of the black body. Aha. Oh. Well, and here comes now something interesting in the game. Betelgeuse appears to be red, so it doesn't, compared to Rigel, which was bluish. In Rigel, we can associate a temperature of about 20,000 Kelvin surface temperature, while Betelgeuse is maybe 4,000 Kelvin. Factor 5 difference. 5 to the power of 4 is quite something. 25 or 25, 600. In the emitted power difference. And what comes into game? We have a lot of red stars in the universe, but Betelgeuse accounts as a red giant. It's a star basically already in the hospice. It's not going to live for long anymore. And when they reach this stage, they expand massively. And the surface temperature is very, very, area is very big, because now the sphere is blown up and the surface of the sphere proportional to r squared. Gets massive. So in spite of having a relatively low temperature, its energy output is still absolute massive, because we still have this A factor in here. Compared to most red stars, which we would call a red dwarf. Maybe 3,000-4,000 Kelvin surface temperature, but very small. Down to maybe 8% of the mass of our sun. remember that for stellar masses, the most reasonable thing to do is just to use the mass of our sun as natural unit, solar masses. That's this 8% is necessary that the star can produce continuously light. Below it doesn't make sense to talk of really of a star. We would talk of what's called a brown dwarf. Oh. Okay. So we learn here again something about if we can measure the absolute power, because we know the distance, we know how much we measure, we know how much has been emitted at the very beginning. And then we can calculate back towards the surface area. If we have the surface area, we have the radius. If we assume it's a sphere. So very useful laws. But here also very important, we have always the same shape. It's just slightly adjusted. Blackbody radiation. Well, in fact, this is, here I can use now some nice words. What we do establish is there is a direct proportionality. Where do we find the maximum as function of this, of the wavelength, of the temperature? We establish a proportionality. But then we need experiment and a certain unit system that we can make an equal sign. And therefore we need basically here this constant. Also, we had here on the right hand side 1 over Kelvin. We have here on the left side the wavelength, dimension of a length of meter. On the right hand side we have 1 over Kelvin, what means we need this constant also to have the units, which must be meters multiplied with Kelvin, so that Kelvin cancel away, and executing the calculation we directly have converted this inverse temperature to a length. So that's the nature of physics law. We always need this constant that depend on the unit system. So we usually use the standard international or international standard system. Can also go back to the old imperial, doing everything in yards, stones, and whatever ounces. For me as continental, of course, absolute a nightmare. So this is one thing, and the rest, the number itself, we need to establish via experiment. This is something we would again assume to be one of these universal constants. We measure it here. We assume it's the same one on the surface of Betelgeuse. So 500 light years away. We would assume it's the same at the other side of our galaxy. We would assume it's the same in Andromeda. Or not for sure, but yeah. Then the second law, the Stefan-Boltzmann law, gives us, of course, another constant, Stefan-Boltzmann constant. By the way, these were two different people. Stefan is here family name, usually it's a first name, so it's a bit unlucky. I always thought it's the same guy, always one guy, and one not, in which relation he was to Ludwig Boltzmann, big man in molecular gas theory, until I realized, or at some point somebody told me, stupid idiot, it's two guys. Yeah. Again, we need this here basically for the units. So these laws and the blackbody. Blackbody is now much different from what we had previously. Previously, we had basically these very sharp lines at a given wavelength or frequency. They can easily convert it via C equals frequency multiplied with wavelength. So speed of light equals. Yeah. Okay, now established a couple of laws, and here we see we basically have this continuous distribution, which means we always see the rainbow. Unless the temperature is so low that the distribution really just starts here and this long wavelengths. See, long wavelengths, do you remember what this was? Indeed, infrared. Low wavelengths, high energy, ultraviolet. Now this, I know it's confusing at the beginning, what lambda frequencies, this is all this, what is wavelength, what is frequency, what is the major difference. Directly from atoms, we get this line spectra, we know what is there. From the black body, we get this continuous spectrum, we know how hot is it, and if we can measure, if we know the distance, we directly can measure the surface area, A. Or if we know the surface area, we know how much, what is the power that is emitted. We can look, what do we receive? We know the distance. So, well, interestingly, people have established this, all these laws, this Wien's law, Stefan, Boltzmann law, they were established 1850. Yet people could explain basically here, this side and this side, but not the entire range within one theory. They were struggling until basically one guy came along and made a completely stupid assumption. Before, energy was almost continuously distributed, and this guy said we have it only in packages. If you make energies very small, they are packages. It's just we don't realize them because the package difference, the step height is so small, we usually don't see it. Max Planck. Or that the energy comes always in packages, h bar multiplied with the frequency. It's like Einstein's energy equals mc squared. This is even simpler, this formula. It seems that the simpler the formula, the more important it is. And with this assumption that basically we have the things that can oscillate, but only with very special frequencies, not with all frequencies. We got basically this shape explained. Published it. Well, I don't want to know how much insults he got. And now you see basically that's Max Planck when he was a student, 1878. Students were then nice looking, but in the end they were all hardcore drinkers. That was 1878, and this is 1901 when he discovered basically quantum mechanics. You see what quantum mechanics does to you. This explains probably my appearance. And well, later on he did but more distinguished. And maybe you heard from the importance that he has. In Germany, there's a big institution called the Max Planck Society. It's for basic research. Getting there, director position, you are the winner because you have no bosses anymore. Except when you leave more than 2 weeks, then you should tell the secretary. But otherwise, you can do with your time what you want. But to become one of these directors, you need to publish and you need to be excellent. Yet, given all the resources they have and the time that they are allowed to concentrate, mostly just on research, I'm a bit disappointed for the number of Nobel Prizes that come out. Okay. So, but now to come back. Basically, every time we have a body with different temperature, we get this Planck spectrum. If you look back, the old light bulbs We had tungsten wire which got heated by a current flowing through. You got a nice Planck spectrum out. And depending on the current and the temperature, you also change by the temperature of the bulb. Okay, so there it was realized. Then if we look at our sun, so the yellow stuff is the stuff that we observe above the atmosphere. It looks very good, like a black body. Of course, there are surface effects, and we have what we see. There is a bit of this. The outer layers are different, but we can see as through different layers. So this is basically a superposition of different temperatures that we see. It's not the Planck spectrum of one temperature, but at least we see it. It works out relatively well. So, so again, and then now we understand basically why do we see our colors? Why did our eyesight adjust on this visible part of the electromagnetic spectrum? Why don't we do it like snakes, which are night active? They don't have sunlight. Or most of them are probably night active in hunting. They use infrared. So basically this part, the heat radiation that comes away from the body. Why do we use the visible part? Well, there's most light particles all around. So this here is much higher than if you take the same range here. This is 10 times higher. So we have 10 times more available. We have 10 times more light particles striking the nerves in our eyes than in the infrared. We make a much better use of what is there. Nature had simply, I think, 3.8 billion years since the first life formed on Earth at the moment, time to adjust us. But since we're mostly day active, obviously we go for this part of the electromagnetic spectrum. So again, you see it's a bit like in quantum mechanics, we have boundary conditions. And that causes the system to adopt certain values to maximize. Okay. And well, then comes the atmosphere. What does the atmosphere do? It absorbs. There is gas. Gas, most at the very top, there's this ozone. Thank you. Ozone has a strong absorption. So this O3 has strong absorption of this high energetic stuff. Oof. We don't want to have skin cancer. In fact, when I was about your age, everybody was concerned about the ozone hole in Antarctica. When I joined the army, a mate, he just have been to South America, to Chile. And he said occasionally you could pick up the rabbits just from the ground because they were already blind. Apart from the skin, what is affected is your iris. I think that's, how to say, you can't see through anymore clearly. Many of these rabbits had this. And he said you need sunblock 30, and even then you occasionally got underneath the t-shirt still a sunburn. So, but mankind realized the problem and we reacted and we solved it. For once, we really, usually human beings are nice on an individual basis, but as a herd, we are terrible. What we can do there, boom. Okay, so, and for once we acted and solved the problem. So we reduced this FC, I don't know, carbon chlorides, carbon halogenides, basically the stuff we use in dry cleaners and formerly in fridges. We reduced the use hairspray, of course, in the 80s, it's our stupid hairstyles. Well, we reduced it, and now the ozone is rebuilding. Well, how is the ozone built? You have O2 molecules, and on top, UV light comes along, cracks one of these molecules. Then you have free oxygen, and it might attach to another oxygen molecule. Then you get this O3. It's not healthy to have it here because usually you have an electron too much. This means it likes to react like hell. If it comes into your lung, it likes to react, and not too healthy. Okay, so this is the O3 taken away. But then we have, of course, also water. Here, all these dips where basically the entire radiation is absorbed. Water. And then we have a bit of carbon dioxide. And since this here is changing, the absorption changes, it gets a bit more and more. In the atmosphere heats up a bit more. That means it gets hotter, it can hold more water. This here gets more taken away, more absorption in the water. It's getting even hotter. The greenhouse effect. Okay, so what we see here is basically if we fit such a black body spectrum, our sun has a surface temperature of 5,250 degrees Celsius. It's 5,500 Kelvin. But we also see if we want to observe in the infrared here, we have a problem. Here we almost come to the millimeters, micrometers, and soon we are in the millimeters. But here we have problems. We have basically holes in, massive holes. Now visible, this still looks reasonable. That we get all wavelengths more or less through. Of course, if you want to observe blue, we have to correct for this absorption. Or we have to avoid as much as possible the atmosphere, especially where it's dense, what means near the ground. If you go high mountain, the atmosphere becomes far less dense. Oh. So a reason why not to observe here at the ground. We go to mountains, but then we see UV, X-rays. X-rays usually also a couple of meters in there. So gamma rays, fortunately, also. Even this super high energetic gamma rays occasionally comes from sky. What they do, they ionize. Then you make basically charged particle and secondary radiation. So again, absorbed, lost, quickly lost, fortunately. So all this hard stuff we cannot observe as consequence. You cannot have in an Earth-based observatory. Where waves that obviously again pass through the atmosphere, well, when you switch on the radio, obviously there's music coming out, annoying advertisement, and so on. So obviously radio waves make it through the atmosphere. We can do radio astronomy Earth-based. For infrared, for UV, for X-rays, for gamma rays, we should leave the Earth's atmosphere. What means we need to pack our observatory on a satellite. Satellite means it's immediately costly. Just to transport, if you think, what does it cost nowadays to bring one of these space tourists into space? Easily 20 million. Then you calculate it down per kilogram. Ooh. So then you, from 80 kilos, you go back to a ton or 2 tons. Costly stuff immediately. Of course, and then you need to develop all this technology, which is usually prototypes. You need not just to develop it and hope that it works when you bring it in space after all this shaking during the start and whatever. You have temperature differences. Another problem in space, the electronics is usually exposed to radiation, gamma radiation, particle radiation that is otherwise observed by the atmosphere. The electronics get basically wrecked. The semiconductors get shot through with time or over time and all these problems. But you need to do it, otherwise there's no chance. And this is nicely shown here in this plot, where you basically see the absorption as a function of the height in the atmosphere. And here we go along the electromagnetic spectrum again. The high energy stuff, or short wavelengths, high energy, long wavelengths, low energy. And what we see, what is coming through is radio wave, microwave is partially absorbed. It's not so good. Infrared, well, the very, very near infrared maybe, but the rest, not. UV, fortunately gone, X-ray guns gone arrested. So everything needs to go in space. And what you see here, this here is the Spitzer Space Telescope at the moment. And I should check this out. So the Space Webb Space Telescope for the infrared. This is the Hubble Space Telescope. Well, here we wanted to avoid all these disturbances from the atmosphere, because what is happening, you have an atmosphere, light ray. If you have light going from one medium to another medium, which has a different diffraction index, a different density, like air to water, you get this bending of the light, like in the prism. From air to glass and back, you get always this bending. If you want to have a picture, now you have a wind, some wind, its density changes in the atmosphere. You get this fraction. You get this light gets bent away. This kills your optics. And if you want to observe a very faint object, what means you need to collect light for the entire night. You have, of course, the problem that you rotate underneath. You need to follow your observatory exactly. Every vibration of the observatory makes, of course, already a problem. So if you have a bit of somebody jumps around nearby, rabbit jumps around, you get a bit of a shake. All this kind, you need to decouple your system completely. And then if you have constantly the wind going, moisture is absolute. It's horrible. Of course, not only clouds, but also moisture. That's why people, for example, wanted to build an observatory where you don't have moisture in the air. Because if it was moisture, it was already snow, it snowed already away. The center of Antarctica. Oh. So you have their best conditions. It's so cold, there is no more liquid. That's why people at the beginning of the 90s have sent up this basically the size of a school bus observatory into space, Hubble. And this here is Chandra X-ray telescope, that we have X and Newton and whatever for X-ray studies. For UV, there is now also something up. I always forget what the name is. And gamma rays, this is the integral satellite. So we want to observe as much as possible, as you have seen it from the very beginning. But there is a necessity to go for satellite. Satellite means limited space. You have problems if you have to maintain it. And But even building something on a high mountain to escape, of course, a few things. If you build ground-based, oh, good, this question here, but we basically answered already. Question: why has nature adjusted our perception to the visible part of the EM spectrum? It's here immediately clear. Otherwise, we would see in the radio wave. But for radio waves, you need always a bit of bigger antenna. So could have 2 antennas. Why 2? Well, only if we have a different speed of light. This means different arrival times. The light from the same object has different arrival time, usually when it comes to your eyes. This little time difference is enough for our brain to calculate. Yes, it was under this angle. It came with such a difference, it must be so far away. This type of distance. Our brain is amazing. If we would have such scientific instruments. Just look at autonomous driving. Of course, most people also make accidents. I shouldn't. I'm a horrible driver. But at least I'm aware I drive accordingly. So I'm looking forward for autonomous driving. Especially my generation is going to be hell, because there are many of us, of my generation, have never experienced that you can move without a car. At some point, I lived in the US and had a girlfriend. She wanted to go to the gas station 300 meters down the road. And she took a 3-ton truck. Oh, it's when people don't even realize it. Wonder why they have these legs. Oh, yeah. So before I get now completely lost, okay. But coming back, we have seen why our eyesight has adjusted itself, and 2, of course, to get these distance impressions. Why not 3? It costs a lot of brain power. Brain costs a lot of energy of our body. Again, nature says 2 are enough. 3 is just a waste of resources. It would be nice to have another pair of eyes at the back, but your head must be bigger because you spend already so much of your brain for 2 eyes. And it doesn't really give you benefit in the moment you have ears that can warn you for the back, or you have a friend that watches your back and you can turn your head around, or your body stuff is done. Okay, so obviously it's something also about efficiency. What is there mostly that we want to use? Then we want to have it mostly undisturbed. Well, going here, up here, has of course also other advantages. We come back later. But we have seen now that the amount of photons we get is obviously something crucial. So it might be beneficial if we have technical devices that help us to gain more light to come to our eye or to the photographic plate, or nowadays to the array of CCD cameras. And about telescopes and observatories, we're going to talk in the next video. But now again, I face the usual problems that my coffee is almost empty. So see you in the next video. Oops.